Sometimes you'll need to manipulate scientific notation. So, for example, you get given the frequency and the wavelength of a whole lot of electromagnetic waves. Interestingly enough, when you multiply the frequency and the wavelength of any electromagnetic wave, you get the number 3 times 10 to the power of 8. And you can take a look at the fact that as the frequency gets bigger and bigger, so the wavelength gets smaller and smaller. And I can clearly see that when I put it into a table, hertz at the heading, meters at the heading, where I can see that this power of 10 in scientific notation gets bigger and bigger. You can't see it so easily in the wavelength when I go meters, centimeters, millimeters, micrometers, nanometers, picometers, but it is much easier when I convert all of those into meters, and I can then see quite clearly that my exponent on the 10 is getting smaller and smaller and smaller, negative 11, from negative 1 all the way down to negative 11, which means that this number is becoming 0,000000002. All right, what we now need to do is, let's say we're asked to plot a graph of frequency versus wavelength. What's helpful sometimes when you have these weird numbers with the times 10 to the positive something or times 10 to the negative something is to try and standardize the times 10 to the power of. So you don't write it in proper scientific notation. Watch what I mean. Let's just take these 4 over here where we can get it into some sort of semblance of control. It starts to get too big here and too small there, so let's just use the first 4 numbers, and even then it's going to be very difficult to graph, but it's just to give you an illustration of how you would work it. So instead of 5 times 10 to the power of 8, I go 0,05 times 10 to the power of 10. In other words, I've moved this comma back to get to an extra 100 on the 5 to the 10. Let me show you what I mean. I'm going to say 5 times 10 to the negative 2 times 10 to the 8 times 10 to the positive 2. The 10 to the 8 and 10 to the 2 become 10 to the 10, and the 5 to the negative 2 becomes 0,05. If I do that standardly, I get times 10 to the 10 all the way through for the frequencies. And I can do the same thing with the wavelengths over here. So I can say 6 times 10 to the negative 1 times another, sorry, I'm running out of space, 10 to the negative 1. Those two together, the 10 to the negative 1 and the 10 cancel each other out in the same way as the positive 2 and the negative 2 cancelled each other out. But I can write this differently as 60 times 10 to the negative 2 times 10 to the negative 2. So what I've done is I've tried to standardize the times 10 to the same exponent in all of them, and then see if I can graph these pieces of data over here, just the number, because again I've got some sort of standardization at the back. I'm in the same unit and the same times 10 to the. So if I take that information and try and put it on a graph of y versus x, frequency versus wavelength, I can say frequency in hertz times 10 to the 10, and then I only need to make my graph go from 0,05 to 3000. So from 0 up to 3000. Same thing on the wavelength. I can say times 10 to the negative 2 and then only worry about getting as high as 60, 10, 20, 30. Ideally, I've made a mistake here, you should have a 0 over there. Okay. Now to plot those points is pretty darn difficult, to be honest. You need the biggest piece of graph paper ever. But if you had 60, you would be on the 60 line, and at 0,05 you'd have something more or less there. And then 1 times 10 to the negative 2 brings you all the way to about here. And then 0,1 times 10 to the negative 2 brings you even closer. And 0,01 brings you even closer. And by that stage, you're at 3,000. So you would land up with some sort of a, something that was a bit like that. But you need a much bigger graph paper to do it justice. What's important is that you can see how to put that sort of data onto an axis. If I were to give it to you in a test, I wouldn't give you such spread out data. I'd give you something much, much narrower, but you would need to know how to use the times 10 to the 10 as a standard on the axis so that you have more manageable numbers actually written onto the axis. Let's take a look at some of these examples over here in terms of unit converting, just some extra practice. We've got 15 minutes going into seconds, so all I'm going to do is multiply that by 60, and I land up with 900 seconds. And when I take 210 seconds and I divide it by 60, I get my 3.5 minutes. When I'm going from kilometers into gigameters, kilo is times 10 to the 3, giga is times 10 to the 9. So I have got 6 hops along on the line there. Kilo is small when compared to giga, so I'm going to go from a big number to a small number, which means I need to divide. So it's 46 times 10 to the negative, that's the dividing, and 6 on the number line. And when I write that properly into scientific notation, I get 4,6 times 10 to the negative 5 gigameters. Centimeters into meters, I am going to say centi is small when compared with meters, which is big. So my unit is going to go from big, sorry, my number will go from big to small. Centi is times 10 to the negative 2. Meters is 0, so we're going to have 2 hops. 745 times 10 to the negative, because I'm dividing my number, and it's 10 to the negative 2. That turns out, by the way, to be very conveniently 7,45 meters. Then you have got 42 milliliters into centimeters cubed. A milliliter is a centimeter cubed. A milliliter is not a liter, though, and we now need to say I'm going from milli to liters. I'm going to divide by 1,000, 0,443 liters. When I go from millimeters cubed to decimeters cubed, I am going from millimeters cubed to centimeters cubed to decimeters cubed, which means that I am going to divide by 1,000 and then divide by another 1,000, which means I'm going to divide by 1,000,000, and so that becomes 93 times 10 to the negative 6, which turns out to be 9,3 times 10 to the negative 5 decimeters cubed. And meters cubed to centimeters cubed, I'm on 2 hops again of timesing by 1,000 this time, because I'm going from a big unit to a small unit, so I'll go from a small number to a big number. So I go 0,06 times by 10 to the power of 6, and that'll turn out to be 6 times 10 to the power of 4 centimeters cubed. Grams to kilograms, not difficult at all. It's divided by 1,000, and we should be fairly familiar with that. They don't say I have to give that in scientific notation, so it's fine. Then I've got nanograms to micrograms. Nano is times 10 to the negative 9. Micro is times 10 to the negative 6. So that's going to be 3 hops that I have to do. A nanogram is smaller than a microgram. A nanometer is smaller than a micrometer. So my number is going to go from big to small, which means I have to divide. So I'm going to take 0,998 and times it by 10 to the negative, because I'm dividing, and 3 because of the 3 hops on the number line between the two. And that turns out to be 9,98 times 10 to the negative 4 micrograms. Milligrams into grams is just millimeters into meters, which means that I need to divide by 1,000, so it's 0,032 grams. And then we've got the 2 more complicated ones of going from kilometers per hour into meters per second, and meters per second into kilometers per hour. Remember, do it in 2 steps. 100 kilometers in 1 hour is equal to 100,000 meters in 3,600 seconds. And I land up with 27,78 meters per second. And in the second one, I say 50 meters per 1 second is the equivalent of 0,05 kilometers divided by 1,000, and 1/3,600th of a second, of an hour, sorry. And if I write that slightly differently, I can tip and times, and I get 0.05 times by 3,600, and that turns out to be equal to 180 kilometers per hour.